Okay, so somebody asked me a question about this homework problem, and I figured I'd make a video because it's easier, and that way everybody can see it. So the problem is to determine all bipartite graphs G such that G complement is also bipartite. So if you recall the definition of a bipartite graph, which is it's a graph whose vertices can be split into two sets, two non-overlapping sets, such that all of the edges of the graph go in between one set and the other set. Every edge in the entire graph has one end in one set and the other end in the other set. I usually call the two sets A and B. So for example, this graph is bipartite if I just let this set of, it's just a set of one vertex, and I'll call that one A, and I'll call this one B, and every edge in the whole graph goes to A to B. Or every edge in the whole graph has one end in A and the other end in B. This graph, I could also say is bipartite and I would say that every edge goes from A to B. There are no edges, but it's still a true statement that all of the edges, and of course there are none, they go from this set to that set. Of course, I could say whatever I want about all edges of this graph because there are no edges of this graph. The important thing about being bipartite is that there aren't any other edges. There's no edges with both ends in A or with both ends in B. Okay, so these two graphs right here are examples of bipartite graphs whose complement is also bipartite. These two graphs are complements of each other, and they are both bipartite. So for these will be part of your answer. Let's talk about slightly bigger graphs. Like we talked about two vertices just now, let's talk about three vertices. This one is bipartite. If I let this set be A, this set be B, every edge has one end in A and the other end in B. Is this one bipartite? This is a little bit of a trick question. The answer is yes. This graph is bipartite. And if you think the answer is no, I'll bet I know what you're thinking. You're probably thinking that this is A and this is B, and here I would have an edge with both ends in B, and that's no good for a bipartite graph. But the thing is, it doesn't have to be that this is A and this is B. For a graph to be bipartite, there just needs to be some sets that I can split the vertices into, split it into two sets such that all of the edges go from one set to the other. The two sets, these are called the partite sets, or it's the bipartition of the graph. And what I'm telling you is the bipartition of G doesn't have to be the same as the bipartition of G complement. They can both be bipartite even if they don't have the same partition. And it's a little bit misleading to call it A and B and A and B. Of course, you can do that if it's the same partition on both sides, but maybe I'll give them different names here. If I call this set A prime and this set B prime, once again, all of the edges have one end in A prime and the other end in B prime. So here we have another example of two graphs. They're complements of each other, and each one is bipartite. So these two graphs will also be part of your answer. Let's talk about these two at the bottom. And I guess Yeah, actually, maybe I should give these like, I just realized that I'm calling all of these G. Maybe I'll call it G1, G2, and G3. So we talked about G1 and its complement. We talked about G2 and its complement. Let's talk about G3 and its complement. G3 is bipartite. It's very easy for a graph that doesn't have any edges to be bipartite. I can kind of do whatever I want. If I call this A and this one B, once again, all of the edges, and once again, there's no edges, but all of them have one end in A and the other end in B. So sure, this is bipartite. Is its complement bipartite? Well, I mean, I can't just use the same partition that I used. I can't call this single vertex A and this pair of vertices B, because I would have this edge with both ends in B. But then on the last example, we tried a different partition and found one that worked. So how do we know how to find a partition that works for this, or if there even is one? Because keep in mind, not every graph is bipartite, so it might not be possible for this graph. So let me tell you, this graph is not bipartite. A bipartite graph can't have three vertices that are all adjacent to each other, also known as a triangle, because imagine that we had our two sets, A and B, and that they were a valid bipartition of this graph, meaning every edge has one end in A and the other end in B. Then say if I look at these two vertices, one of them's got to be in A and the other's got to be in B, right? So maybe this one could be in A and this one could be in B. But however it is, they would have to be in opposite sets. One's in A and the other's in B. But then where can this one be, right? If this one's in A, then this one would have to be in B, because every edge is supposed to have one end in A and the other end in B. So since there's an edge here and this one's in A, this one would have to be in the other set, B. But then this edge is a problem because I have B here and B here. So there's no way to do this. There's no way to split these three vertices into two sets such that this will be a valid bipartition. These two have to be in opposite sets. Of course, I could say this one is in B and that one's in A, but then that wouldn't help. There's just no way to do it. And keep this in mind as you attack this problem. I gave you a few graphs that are going to be on your list of graphs. I didn't give you all of them, and I'm trying to hint right now at how you can prove, once you find all of the graphs that are on your list, like your list of graphs that are bipartite and their complements are bipartite, you can prove that there aren't any more graphs by using this type of logic. So a graph that has a triangle in it can't be bipartite. Just remember that.